We've defined sequences, and we've specifically addressed the issues of an arithmetic progression and a geometric progression. Let us now move on to a series. A series is defined as the sum of the terms of a sequence. This means in practice that a series is the result of adding all the terms of the sequence together as follows: A1 plus A2 plus A3 plus either to indefinitely, or if there is the length of the sequence is limited, this will be adding up all the limited values of the sequence to form the series. In mathematics, we have the symbol sigma. Sigma means the sum of. So what we can do, we can thus write this above series, we can write compactly as follows. We can say the series is equal to the sum of n equal to 1, where n is our nth term, to infinity, if we have an infinite number of terms of an is the nth term. In other words, we just sum all the terms together as shown here. Very simple and straightforward. If we are dealing with finite series, we write the series as follows. Then the series is equal to the sum of n equal to 1 to k, where k is the number of terms within our sequence of an, and this defines a finite series. This will define an infinite series. Okay, let us move on to an arithmetic series. Now, specifically, the sums of the element of a finite arithmetic series is called, specifically, the sums of the elements of a finite arithmetic sequence is called an arithmetic series. Thus, if an arithmetic series has n terms, we can write the sum of these n terms as follows. Just remember something, we remember the general formula for the nth term of an arithmetic sequence is an is equal to a1 plus n, where n is the nth term, minus 1 times d, where d is the common difference. Therefore, we can write, using this general formula of an arithmetic sequence, we can write for the arithmetic series, we can write a1 for the first term plus a1 plus d, because d is the common difference, so the difference between the first and the second term of an arithmetic sequence is a1 plus d, plus a1 plus 2d, where 2d gives the third term, because d is the common difference. We can continue this until the second last term. The second last term will be given by a1 plus n minus 2d, and the last term will be given by a1 plus n minus 1 multiplied by d, the common difference. Now the last term is easy to understand. This is just an implementation of our general formula for an arithmetic sequence. Straightforward. Now if the last term is a1 plus n minus 1d, obviously the second last term will be n minus 2 times d, and the third last term will be n minus 3 times d, so on until we end up with the first term being a1. So this is a method to write the arithmetic series of an arithmetic progression. Now, furthermore, we can use the formula for the nth term. Now, the formula for the nth term is given by this value. a1 is equal to an is equal to a1 plus n minus 1d. We can then just manipulate this formula as follows. Let's manipulate this formula and make a1 the subject. We can say then a1 is equal to an minus n minus 1d. We've just manipulated this basic formula for an arithmetic sequence or an arithmetic progression to determine a value for a1. If we then continue this process, we can then similarly determine for a2. a2 is then equal to an minus n minus 1 plus d. Why can I say this? If I say we know that the common difference for an arithmetic sequence between the first and the second term is given by d, or between any consecutive term is given by d. So if I have the value of the first term, which is this value here, we determine this value to be the value of the first term. If we just add d to the first term, we will have the value of the second term. And we can write this, then we can then say that A2 is equal to AN minus N, excuse me, we need to put a D there, minus N plus D plus D. Therefore, this then simplifies to AN minus N plus 2D. So we've found ourselves an alternative expression for the value of A2. So we can continue this process, and if we use this method for writing down the terms of an arithmetic progression, we can then write another form of an arithmetic series as follows. We determine the first term is equal to AN minus N minus 1 times D. We also said the second term will then be AN minus N minus 2D. It is logical because we just added the value of D to that value. So in other words, we ended up with plus 2D. We proved this part of the equation by this simple expansion here. We can continue this until we have the third last term, which is AN minus 2D. The second last term will be given by AN minus D, and the last term will be given by AN. Now this is obvious. We know the last term is AN. We know the difference between the last term and the second last term is the common difference. So if we have the last term and we subtract the common difference, we will find the second last term. If we have the second last term and we again subtract the common difference, we will find the third last term, and we will continue until we end up with the first and the second terms as defined here. Note now that we have two equations, two different equations giving us the series of an arithmetic progression. Let us repeat these two equations. The first equation we derived was Sn is equal to A1. The second term is A1 plus D, right? Because the difference between the first and the second terms is the common difference plus D. So if we just add the common difference to the first term, we will find the second term. The third term is given by A1 plus 2D, because adding D to the second term, which is the common difference, gives us the third term. Continuing with this, we will find the second last term to be A1 plus N minus 2 multiplied by the common difference. And the last term is obviously just our basic formula, A1 plus N minus 1 D, this is the basic definition of an arithmetic progression. The second formula that we derived states the following. Let us just repeat it here. AN minus N minus 1 D plus AN minus N minus 2 D plus, until we have AN minus 2D plus AN minus D plus AN. Now what we do now is we add these two equations together. But if we have a look at these equations, we see that we have in the second term of the first equation, we have A1 plus D. In the second last equation, in the second last term of the second equation, we have AN minus D. So if we add these two equations together, the D's will cancel. This D will cancel with this D. This 2D will cancel with this 2D. So what we can say that all terms involving D will cancel. Thus, if we add these two terms together, we say that 2Sn is thus equal to, now if we look at A1, in the first equation, A1 will add with A1, will add with A1, will add with A1, and obviously because there are n terms within an arithmetic progression, we will add A1 together n times. So obviously the first term here will be in A1. We can also see from the second equation that AN is added to AN, is added to AN, is added to AN. So obviously from this equation we can see that AN in the second equations will be added together in times. So we can say in AN, all the terms involving D will cancel. So we find that 2Sn is equal to NA1 plus n times AN. And we can simplify this equation by writing Sn is equal to n over 2 multiplied by A1 plus AN. And we have a very good and simple common form of determining the value of an arithmetic series based upon an arithmetic progression. Now again, let us derive another form of Sn, which is the arithmetic series. Let's start with the nth term, which is the basic definition of an arithmetic progression, which is given by an is equal to A1 plus n minus 1 multiplied by the common difference D. And let us substitute this equation into the above derived equation. In other words, we substitute An with this value of An, and then we reach Sn to be equal to n over 2, A1 plus n minus 1 multiplied by the common difference, which is D. And if we simplify this equation again, we find that this arithmetic series is given by n over 2 times 2A1 plus n, which is the nth term, minus 1 times D. In other words, this gives me if the arithmetic progression consists of n terms, this will be the value of the nth term. That is basic definition of our arithmetic progression. Now this formula gives the sum of n terms of an arithmetic series. Now furthermore, using the mathematical symbol sigma, which this symbol is defined as the sum of, we can write for Sn is equal to the sum of j is equal to n from j equal to 1 to n in A1 plus j minus 1 D, where D is the common difference. If we look at this equation simply makes logical sense, because the definition of an arithmetic series is the basically the summation of all the terms of an arithmetic progression. And starting at j equal to 1, this will give me the form of my arithmetic series. In other words, j1 will give me A1. If j is equal to 2, I will have the second term, and so on until I have j equal to n, and that will be my final term. So this is a very simple and very powerful method to write the arithmetic series of an arithmetic progression based on the basic formula of an arithmetic progression. Let us now define. Let us define the last term in an arithmetic sequence. Term in an arithmetic sequence. Let us define the last term of an arithmetic sequence to be k. Okay, and then using Sn is equal to n over 2 2a1 plus n minus 1 d, we derive this formula on the previous page. Right, this is the last formula on this page. If we say now that the last term in an arithmetic sequence is k, then we can write this as well as n over 2 multiplied by a1 plus n minus 1 times the common difference. Now we said this value here, that is the last term per definition of the arithmetic progression formula. So we can replace this with k as follows, and we have another form of an arithmetic series as follows. Sn is equal then to n over 2 multiplied by the first term plus the value of the last term of the arithmetic progression. A very simple and straightforward formula, but also very powerful. Now that we have done the basic fundamentals of an arithmetic series, let us do an examination example of an arithmetic series. The examiner gives us the following arithmetic sequence. The sequence he gives us is 3, 6, 9 up until 2, 6, 4. And then the question by the examiner is as follows. He wants us to determine the number of terms within this arithmetic progression. Now the first thing we can do is we can see that the difference between the first and the second term is 3. The difference between the second and the third term is 3. And that leads us to the logical and easy conclusion that the common difference of this arithmetic sequence is 3. Thus we can say D, the common difference, is equal to 3. A very easy derivation that we've made. Let us again repeat the general formula for an arithmetic progression. It's given by an is equal to a1 plus n minus 1 times d. We know that an is 264. We've been given that by the examiner. We know that a1 is 3. That's also been given to us in the system. We know that the common difference is 3. So we just need to find n, which is the number of terms, which is just an easy substitution within the general formula. Therefore, 264 is equal to 3 plus n minus 1 times 3, which is the common difference. Solving for n, we find n to be 88, and thus we have 88 terms within the sequence. The second question, more related to an arithmetic series, is find the sum of 88 terms, which is the application of an arithmetic series theory. Find the sum of 88 terms. Now what we do is we know that the sum, we derive the sum of an arithmetic series as n over 2 multiplied by a1 plus k, where k is the value of the nth term. N is equal to 88, so a1 is given, if we look at the previous page, a1 is given by 3, and k is given by 264, is also an input from the examiner. So this expression for an arithmetic series of an arithmetic progression, we just again need to substitute n for 88, a1 for 3, and k is the value of the last term within the arithmetic progression, which is 264. And when we solve the solution, we have 11748. And this is just then a very easy implementation of an arithmetic series, but it does show us the basic fundamentals of determining the value of an arithmetic series.